How can we solve x prime equals a times x if a is diagonalizable? In a linear algebra course you may have learned how to do this. In this video we will review the steps. These steps will give us an easy final expression for n independent solutions. We recommend to memorize this final expression. From now on we will often use it without doing all the linear algebra steps in between anymore, because this will allow us to do our computations a bit more fast and more smoothly. So how does it work? So we're looking at x prime equals a times x, where a is diagonalizable. So that means that we know a equals p times d times p inverse, where you put the eigenvalues on the diagonal to get d, and where p consists of the accompanying eigenvectors. And those eigenvectors are independent. So p is invertible. So that is what it means that a is diagonalizable. So how do we solve our problem x prime equals ax in this case? Well, we use the following trick. X prime equals a equals p d p inverse times x. Then we multiply with p inverse on the left. So we get p inverse times x prime, because p inverse does not depend on t. We can take it inside the derivative, equals d times, and here we have another p inverse times x. So p inverse times x prime equals d times p inverse x. So we define a new variable y equals p inverse times x, and we obtain y prime equals d times y. Now we can write down the solution immediately. Y of t equals e to the power dt times y of 0. Then again, to avoid clutter, we take n equals 2 for convenience to see how this looks like, the solution. Well, e to the power dt in the 2 by 2 case is just the lambda 1 and lambda 2 on the diagonal. If you take the exponential, you just need to take the exponential of that, as you learned in your linear algebra course. So y of t equals this e to the power dt times some initial condition. And you can write this as a factor c1 e to the power lambda 1t plus c2 times e to the power lambda 2t. So there we have our y of t. Now we can compute our x, because x equals p times y, so x equals p times y. We again have matrix times vector, so we get this vector times the first vector here, plus this vector times the second vector here. So there we have our solution x of t. c1 v1 e to the power lambda 1t plus c2 v2 times e to the power lambda 2t. So if you would have a bigger matrix, you simply get more of those, c3 times v3 times e to the power lambda 3t, and so on and so forth. So to summarize, we found now independent solutions. Here our first independent solution, x1 equals v1 e to the power lambda 1t. Second independent solution, v2 times e to the power lambda 2t. So those are our independent solutions if a is diagonalizable, and you can check that they're indeed independent by checking the Wronskian. So we take the determinant of x1, x2, and you can rewrite it as determinant of p times determinant of this matrix with the exponentials. Well, determinant of p is non-zero because p is invertible. We had enough independent eigenvectors because a was diagonalizable. And the second matrix determinant is of course not 0, because there you have only exponentials. So we see that the Wronskian is indeed non-zero. So this procedure will indeed give us enough independent solutions.